When we think about AI, we usually picture some kind of brain floating around in the cloud. But what happens when you give that brain a body? I mean, a real body that can see and move and actually do things in our physical world. Okay, let's get into it. We're going to build a thinking robot, step by step.
This quote, right here, it just hits the nail on the head. This is the whole challenge. It's not just about writing some clever code anymore. It's about connecting that digital mind to physical hardware, stuff that can actually act out here with us. That's the mission of physical AI. So how in the world do you build that bridge?
Well, the journey for any robot starts with a body. But just as important, you have to give it a nervous system, right? A way for all its different parts to talk to each other. Because without that, you don't have a robot. You just have a pile of motors and sensors waiting for a command that's never gonna come.
And that nervous system, it's built on a piece of software called ROS2, which stands for Robot Operating System. The best way to think about it is like a universal translator and a central switchboard for the whole machine. It's this amazing open-source framework that lets the motors, the cameras, and the processors all work together like they're one single coordinated thing.
And here's the really clever part of how RS2 pulls this off. It uses something called nodes, which are like little individual specialists. You've got one that just handles a motor, another one that just handles a camera. They broadcast what they're doing on topics, which are kind of like public radio channels anyone can listen to. And if one node needs a specific answer from another one, it uses a service. It's this exact system that lets the robot's hand know what its eye is seeing, all in real time.
So let's be super clear here. ROS2 isn't the robot's brain, not yet anyway. It's that super sophisticated network of nerves that lets signals fly around the body instantly and reliably. It is the absolute 100% non-negotiable first step to creating a robot that can actually function. Okay, so our robot's got a body, it's got a functioning nervous system, but how do you teach it to do something complicated, like, say, navigate a crazy, chaotic warehouse? You can't just let it loose and hope for the best. It'll crash into everything. The answer is, you don't start in the real world at all.
And this just lays it out perfectly. Trying to train a physical robot in the real world is just incredibly slow. One tiny mistake can lead to super expensive repairs. And hey, depending on what it's doing, it could be flat out dangerous. But in a simulation, a perfect digital copy of the real world, you can run thousands of tests in the time it would take to run one, with zero risk and for way, way less money.
So to build this virtual playground, developers use these really powerful tools like Gazebo and Unity. And these aren't just for making video games. They create these physics-accurate simulations of whole factories or even our homes. But the really critical part is they also simulate the robot's senses, its cameras, its depth sensors, its LiDAR. That way the robot sees and feels the virtual world exactly like it would the real one.
So, let's take stock for a second. We've got a body with a nervous system. We've got a safe, digital world for it to train in. We have all the pieces, well, except for the most important one. Now it's finally time to give our robot a brain.
But that leads us right to the big question, doesn't it? It's one thing to just exist in a simulation. The robot needs a way to process this tidal wave of data coming from all its simulated senses and turn all that information into smart actions. So, how do we make that happen?
Well, the answer comes from these highly specialized AI platforms. For example, NVIDIA's Isaac Sim creates these incredibly photorealistic virtual worlds. And that is so important because the more realistic the simulation, the better the AI's learning will transfer over to the real world. Then you've got tools like Isaac ROS that provide hardware acceleration, which basically supercharges the robot's processors so it can think and react at lightning speed. It's this winning combo. You get realistic data and a high-speed brain.
Okay, so we have a body, a training ground, and a fast learning brain. The robot's complete. Or is it? This is the last step, and this is where things get really wild, like straight out of science fiction. What if we could just talk to our robot, using normal, everyday language?
The real magic here, the secret sauce, is that we're smashing together three things that used to be totally separate into one powerful model: vision, language, and action. And what that means is the robot doesn't just see the world, and it doesn't just process words, it actually connects the two. It understands that a phrase like "pick up the red block" is tied to a specific thing it can see, and that it requires a very precise set of physical movements.
So let's just walk through this for a second. You give a simple command, something like, "Hey robot, could you grab me that water bottle from the table?" A large language model, an LLM, acts as the brain, the cognitive engine. It hears your request, sees all the objects in the room through the camera, and then it comes up with a step-by-step plan. Then, the robot's body just executes that plan. It's the perfect bridge from what a person wants to what a robot does.
So there you have it, 4 clear, essential steps. You start with the nervous system using ROS2, you create a safe place to learn with a digital twin, you power its brain with AI tools like NVIDIA Isaac, and finally, you give it the amazing gift of language using LLMs. Each step is incredible on its own, but when you put them all together, you get the blueprint for a truly thinking robot.
And this all brings us to the final and maybe the most important question of all. The technology to create these intelligent physical robots, it's not a distant dream anymore. The blueprint is here. So the real question for us is no longer how do we build them, but what will we build them for? What problems are we going to ask them to solve next?